Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 22 on the subject of computer organization and assembly language programming. The title of today's session is Data Path of Hack CPU Part 1. Well, we will start today's lecture with a recap of stored program concept by John von Neumann. We will see how information flows among different components of a computer system. We'll talk about the data address and the control bus, commonly called the data path of the CPU. We will try to understand the famous fetch execute cycle in detail and the clash that may exist due to single memory unit. We will discuss different solutions and finally we'll select Harvard architecture, which is a variant of von Neumann architecture for our hack computer. So we have a lot to do today, so let's start playing. Okay, so let me start with a detailed recap of von Neumann architecture and the major components of our computer system. Dear students, as I have said in some previous lecture also about the universality of a computer system, that is a machine with finite hardware that can perform infinite number of tasks from word processing, watching videos, playing games, accessing internet and so on. And this is the fruit of a brilliant idea called stored program concept, which was coined by John von Neumann. Well, von Neumann architecture is shown in this figure, and it is based on a central processing unit interacting with the memory device and receiving data from some input device and sending data to some output device. At the heart of this architecture, of course, lies the stored program concept, and that is this computer memory stores not only the data that the computer manipulates, but also the instructions that tell the computer what to do. So let us talk about this architecture in a bit of more detail. Let me first talk about the memory. Physically this memory over here is a linear sequence of addressable registers, each having a unique address and a value which is a fixed size word of information. And if I talk about the logical concept, logically you can say that memory is divided into two areas. One area is dedicated for storing data, for example the variables, arrays and objects, while the other area over here is dedicated for storing the program's instructions. Dear students, although the data words inside the data memory and the instruction words inside the instruction memory look exactly the same, but they of course serve very different purposes. And lastly, there exists variant to this von Neumann architecture called Harvard architecture as well, in which the data memory and the instruction memory are kept in separate physical memory units, and we will talk about more about this in the upcoming slides. The other component, let me talk about this central processing unit, which is the in charge of executing the instructions of the currently loaded programs. Well, these instructions actually tell the CPU which calculation it has to perform, which registers it has to read or write, and which instructions it has to fetch and execute next. And this CPU, it performs all these tasks using three main hardware components: an arithmetic logic unit, a set of registers, and of course a control unit. Well, dear students, this ALU chip is built to perform all the low-level arithmetic and logical operations featured by the computer. And any function not supported by the ALU as a primitive hardware operation can later be realized by the system software, and of course yielding with slower implementation. Let me talk about the registers. This is the second element inside the CPU. The set of registers may range from a minimum of 2 to maximum 32 maybe, and each capable of holding a single word. Well, these registers are required to store immediate or rather intermediate results, being close to the ALU, rather shipping them in and out of the data memory outside the CPU. So this boosts the performance of the CPU or the overall system. Let me talk about the control unit as well. Dear students, a computer instruction is represented, of course, as a binary code, typically 16, 32 or 64-bit wide, as we have already seen in the previous sessions. Before an instruction can be executed, it must be decoded, and the information embedded in it must be used to signal various hardware devices like ALU registers and the memory, of course, as to how to execute the instruction. This fetching and decoding of the instruction is, of course, one of the main tasks of the control unit. And finally, dear students, computers, of course, interact with their external environments using a diverse array of input and output devices like screens, keyboards, disk, printers, scanners, network interface cards, and so on. And in the previous sessions, we have seen in detail as to how we can interface a screen as an output device and a keyboard as an input device with this computer using a memory mapped I/O technique. Okay, so after having a detailed review of this stored program concept, let us now understand as to how the flow of information takes place inside the computer system. Well, dear students, there are three types of information that need to be passed around the system if this is a system. The first piece of information is the data and the instruction that needs to be fetched from memory to the CPU. And the second piece of information are the addresses of the memory from where we need to fetch the data or the instruction. And the third and the final piece of information are the control signals, that is telling each part of the system what to do, and one important task is to decide which instruction the program need to execute next. Well, all these three types of information are moved inside the system on a bunch of wires called buses: the data bus, address bus, and the control bus. Let us discuss these buses one by one. Well, first of all, let's talk about the arithmetic logic unit. The ALU need to get data on which it needs to perform the arithmetic or logic operation, and after doing that operation, the output needs to be placed back on this data bus so that the result can be stored back in the register or inside the memory. Other than the data that the ALU needs to perform, the ALU also needs to know what kind of operation it needs to perform on the data. This information is sent to the ALU via the control bus. Sometimes we also have to take some information from the ALU and feed it back to control the rest of the system. For example, in case of conditional jump instruction, a comparison is done by the ALU and later a signal is sent on the control bus over here to the rest of the system whether to execute the next instruction in sequence or otherwise. And let me talk about the registers as well now. There are two main categories of registers: data registers and address registers. Data registers need to be connected to the data bus, of course, for both reading and writing purpose. And the second piece of information that moves inside the system are the addresses, of course, and for that we have the address bus. The address registers may contain address of the data part of the memory from where we want to read or write data, and the address register may also contain address of the instruction part of the memory from where we want to fetch the next instruction to execute. So we have addresses over here inside the registers, and they are placed on the address bus. And of course we have the memory, and the last piece we want to talk about, if this address which is provided on the address bus is the address of the data part of the memory, we get the data on the data bus, and if the provided address is of the instruction part of the memory, we get the instruction back on the data bus. Well, this is the view for the data memory alone. It's simple. We place the address of the data memory and we get the data on the data bus. And this view is for the instruction or program memory alone. Here we need to put the address of the program memory of the next instruction to be executed, and that instruction may have data in it, and in that case that data is placed on the data bus. In case the instruction may also need to tell the rest of the system what to do, so the control signals might also exist in that instruction, so they are placed on the control bus. So once again, this is the overall picture of the buses, describing as to how information moves from one component of the system to the other via the data bus, address bus, and the control bus. This is a very basic concept. I have tried that you should have a very fair idea about the general architecture of every computer system, how the information moves from one component to the other. In the later session, inshallah, I will map all this information onto the hack CPU, as to describing as to how the information flows among different components of the hack CPU. Okay, so dear students, now we are ready to go into the depth of the fetch execute cycle, and this slide shows the basic CPU loop, which says fetch an instruction from program memory, execute the instruction, and then repeat. And this is the only thing that a CPU does. So let me talk about fetching first. Well, dear students, we all know that program counter is the register that contains the address of the next instruction to be executed. So we present the contents of the program counter to the memory, and we get the instruction as memory output. Well, the program counter starts from let's suppose 0, and to get the next instruction in the sequence, we simply increment the program counter by 1. So this is normally the default. And in case if we do not want to execute the next instruction in sequence, rather want to jump to a different location, we simply place the address of that instruction inside the program counter, and we go for a jump. Okay, so once we get the instruction, we need to execute it. Well, dear students, the instruction code specifies what to do, which arithmetic or logical instruction the CPU or the ALU need to execute, which memory address to access for reading or writing, and where to jump in case. So executing of the instruction do involve accessing of the registers as well as accessing the data memory. Okay, dear students, can you identify a problem in this slide? Take your time, stop the video for a while, think, just think of a problem over here, write it down on a piece of paper, and then continue this video. Okay, dear students, the problem is that at times we will be presenting a a data address to the memory, and we will be expecting uh, data on this output. Some other time we will be presenting the instruction address to this memory, and we will be expecting an instruction on the output. But since this memory is one address space, so it expect only one memory input and one memory output. So this scheme will not work. So this is a fetch execute clash. So fetching an instruction and fetching data in a single memory unit. So one of the proposed solution is we use a multiplexer at the address input of the memory. 2 by 1 mux, let's suppose. The multiplexer is getting both the instruction address and the data address, and it is outputting either one of these two addresses. At this select input of the multiplexer, we place the fetch execute bit. If this is a fetch, that means we want to get the instruction, so the instruction address will be placed over here. If this is the execute bit, execute part, then we need the data address will be placed over here. Okay, so I hope this idea is clear. Once we place the instruction address, this multiplexer moves the instruction address ahead. We get the instruction at the output of the memory. If the data address is presented to this memory, the output of the memory is data, and this is during the execution phase and this is during the fetch phase. Well, in the fetch phase, we get the instruction and then we need to remember it inside an instruction register. So we need an instruction register. Later on in the execute cycle, we have the instruction already stored in this register, and we can of course work with all the information that we need for the execute cycle using the data memory again, and that is being addressed in the second part of the cycle. So one additional thing that we will be requiring is instruction register to store the instruction for the execute part of the fetch execute phase. Well, dear students, there is, however, a simpler solution as well. We keep two physically separate memory units, one for the instruction and other for the data, and each can be addressed and manipulated separately and simultaneously. And this is a variant of von Neumann architecture called the Harvard architecture. And finally, this is what we are going to implement in our hack computer system as well. That is two physical memories, one over here and one over here. This is the data memory, we will be calling it RAM, and this is the program or the instruction memory, we will be calling it ROM. Okay, so that is all for today's session, dear students. Based on today's lecture background, we will inshallah design the data path of the hack CPU in next lecture. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.